Hi, I'm Kevin O'Toole,
I'm Matt Wismer.
and for our SigSys final project, we did magnetic levitation. Our goal was to levitate a small magnet using a solenoid so that it would stay at a constant height in the air using the current through that solenoid. We have two basic things going on here. The first is what's called the plant, which is our mechanical system, and that is the system that takes in a current and a distance from the solenoid and determines what acceleration is going on in the magnet. So this is our driving function. And knowing that acceleration that is produced due to Lenz's law, we can integrate that twice and figure out what height the magnet is at any given time. And then our control system, the second major system here, can attempt to keep that height at a desired height by adjusting the current going through the solenoid in order to make this a stable system. So our plant looks like this, and it's basically just taking Maxwell's equations and putting them on the magnet and the solenoid system that we have here, and then throwing in gravity at the end. And essentially what we have results in a fourth order system. So the distance from the magnet is proportional to the fourth power of the acceleration there. And one notable thing about this is that the slope is negative, which means that no matter what constant force you put on here, what's going to happen is that when you go away from any fixed point that you have, the acceleration is going to be downward, since there's a negative slope if you are below it, and upward if you are above it, and that means that this is not going to be a stable thing because it's going to push you away from whatever your fixed point is. So then we have our control loop, and we just kept this simple with some derivative control, proportional control, and integral control. Through some experimentation, we figured out that the optimal system was proportional control and derivative control based on the height of the magnet. And so if you were to input the velocity of the magnet, that would be the same thing as proportional and integral control. Using this, we ended up getting a positive slope of acceleration versus distance, which is good news for us because that creates a fixed point and also a stable fixed point. Looking at how the system evolves over time, we can see that the height on the top graph eventually reaches this stable fixed point, and it does so in a way that it never explodes at any point. And on the bottom, you can see the power used by our system, and it's right around 0.8 volts or 0.8 amps running through there, which is a reasonable thing for our solenoid to be powered with.
We can also consider linearizing this system about a certain operating point and trying to control it based on that. What we have in the middle is a gyrator, which is a model of the coupling between the inductor and the permanent magnet, which turns current and voltage into force and velocity. We have our coil, which we know has 60 ohms of series resistance and 250 millihenries, which we can connect to any arbitrary impedance to try to control it. And then on the mechanical side, we have mass as an inductor, and the linearization of Lenz's law produces a negative capacitor, which is why the system is unstable normally. So our control system needs to attempt to negate the effects of that negative capacitor such that the system then becomes stable. The first thing we tried was a proportional and integral control on the velocity, which is equivalent to the control we were using in Simulink. The voltage on the inductor should be proportional to the velocity of the magnet. So we put that through a high-pass filter, C1R1, to bring that into our circuit so that we didn't have to deal with the DC bias. We then amplified that and put it into proportional and integral control stages, and then we added the two of those currents to a bias point, VB, in the bottom left, to create the output voltage that we set across the inductor system. This did not quite work as well as we had hoped. The propagation delay across the 4 op-amps that we have here resulted in there being high frequency noise in the entire loop that was on the same order and actually slightly larger than the signal that we were trying to measure. And of course, if we upped the gains at every point, we would also increase that noise. So that ended up being a showstopper for us, so to speak. What we went with next was a negative impedance model. What we tried to do is cancel out the impedance of the drive inductor and resistor combo in the left here. Doing the math, you see that if we attach a very small inductor to the electrical side, and if that's the only thing, it will keep the capacitor stable, because when you transform an inductor across a gyrator, it becomes a capacitor. So what we wanted here is we wanted to use negative impedances to eliminate the resistance of the coil and lower the inductance to a very low number, and that's what we attempted to do here. Rn sets the gain of the total negative impedance, and then Rc compensates the resistance so that it stays positive and doesn't, because the negative resistance is a positive feedback loop. So we needed to make sure Rc was big enough to keep the resistance just over 0. And when we got those both very close to 0, we got a pretty good result. The impulse response had a second order damped response, in the electrical domain at least. We did not quite levitate the magnet, but this is very good results, showing that we did get a second order response, which off of just inductors and resistors I would not think possible. So having that coupled with the physical system gave us this response, which shows us that we do have some coupling with the mechanical system, so we should theoretically be able to control it. We were not successful in doing that, but with further work, it could be done.